Okay, we're going to be starting section 6.3 here today. This is going to be taking a look at random variables, specific types called binomial and geometric. We're going to be focusing much of this section on binomial random variables. I'm going to talk first of all just about what does it take for a random variable to classify as being a binomial random variable? When we talk about binomial random variables, this is when you are going to perform repeated independent trials, all of the exact same chance process, and you end up recording the number of times that a particular outcome would occur. And so, as often is the case in statistics, we have acronyms to kind of help us remember sort of all the things that we need to check. And so when you're given a certain description of a situation, you want to make sure that it meets all four of these criteria in order for it to be a binomial random variable, because there are specific formulas that only apply to binomial random variables, and you have to first make sure that it meets this criteria. And so the first one is it has to be binary, and by binary we mean there has to be two possible outcomes, okay? So with the situation, it has to be referring to, one outcome would be described as being a success, and then everything else would be considered to be a failure. I should just mention that success does not mean good, and failure does not necessarily mean bad. It's just whatever you're defining, the thing that you're going to be recording, the number of times that it happens, that is a success. The I in bins is independent. We talked about independence here in the last chapter or so. Each trial has to be independent of one another. That means if you know the results of, say, the first trial, it would in no way impact or affect the results of the next trial. The N in bins stands for number, specifically the number of trials that you're going to be performing of that chance process. It has to be fixed in advance, okay? So within the problem, it has to mention you're going to be doing this specific number of trials. We always let a lowercase n represent the number of trials. And then the S stands for the probability of a success. And that has to be the exact same probability from one trial to the next. It can't fluctuate from one trial to another. Once you've determined that the setting is actually a binomial setting, there's an abbreviated way that you can kind of summarize the information, very similar to when we had normal distributions, and we could abbreviate that by stating the center and the spread. If it is a binomial setting, you can put a capital B followed by an N, comma, P. Okay, the N would be the number of fixed trials, and then the P is what we use to represent what that probability of a success is. Remember, that has to be the same from one trial to the next. Okay, so let's take a quick look at a pretty common binomial setting. And that is really just flipping a coin. Okay, it says here, consider tossing a coin n times. So they would have given us a number there and told us how many times we're going to toss. That's the capital N for the fixed number of trials. It says each toss gives either a heads or a tails. That's the B, binary. There are two options there. It says knowing the outcome of one toss does not change the probability or outcome of the other toss. That meets the independence condition. And then if we were to define, say, heads as being the success, then P, the probability of heads, would be 0.5 on any toss. That would be the S for the probability of a success being the same. Okay, so we're going to give you some different situations here at the bottom, and we're going to kind of run through the acronym to see if we think that this particular description is actually meeting the criteria for being a binomial random variable or not. Okay, so this first one says, we're going to roll a die 10 times, and we're going to record the number of 4s that come up. Okay, so whatever you're recording, that is what you're saying a success is. And so a success would be roll a 4, and a failure would basically be not a 4. Okay, anything but a 4. Okay, so it feels like we met that criteria. For independence, sure, if we're talking about a fair die, we could say that each roll is independent of the next. Okay, so it meets that criteria. N, it has to tell us specifically a fixed number of rolls, and it did. There's 10 of those. And then for success, we have to say what is the probability of rolling a 4. Okay, so the probability of rolling a 4 would be a 1 sixth, and that is the same from one roll to the next. So then I could abbreviate this with a capital B, I could put a 10 there for the number of trials, and a 1/6 as denoting the probability of rolling a 4. That's our success. Okay, let's look at number 2 here. Again, going through these same acronyms here. We have a large bin of batteries. There are 50 good batteries, 80 bad batteries. We want to select 8 batteries from this bin. It mentions that we're going to be doing this without replacing the batteries back in between each selection. And we want to record the number of batteries that are good. Okay, so the B would be that a success is what we're recording, so that would be a good battery. That makes a failure a bad battery. Okay, so we're going to define those. Okay, and then the independence condition here, okay, it does kind of feel like this condition is being violated because we're not putting the battery back in. If we're keeping the batteries out, then that's kind of changing the probability from one trial to the next. If I tell you that the first selection was a good battery, then that changes the likelihood when I reach in for the second battery of what the odds are for me selecting another good battery, or for that matter, even a bad battery, okay? The probability is fluctuating and changing each time I remove a battery and I keep it out. So we're going to say that this violates the independence condition, and our reason is because the batteries are not being replaced, okay? Because the batteries are not being replaced. Now, as soon as I get one of these that is being violated, I can simply stop. My conclusion here would be that this is not binomial. Okay, this is not binomial. Okay, so let's go ahead and see if we can try option number 3 here. We're going to roll a die, and we're going to continue to roll the die until we get a 6. We're going to record the number of rolls needed to get the first 6. Okay, it feels like a success here is rolling a 6, and a failure would be not a 6. Okay, we know that when we talk about rolling a dice that each roll would be independent. Okay, each roll is independent of the next. Okay, so now I'm going to move down to N. I need a fixed number of trials, and this is where we get into trouble. It said we're supposed to do this until we get a 6. It didn't specifically say at the very beginning how many rolls we're supposed to do, and one of our conditions for being a binomial random variable is that the number of trials has to be stated in advance. It has to be fixed. So we're going to say this is where this is violating here. A fixed number of trials was not determined in advance. Okay, so again, we would classify that that one is not binomial. Okay, and then our last one here at the bottom is talking about a basketball player here. Okay, it mentions that a basketball player takes 8 free throws in a row. They're going to record the number of free throws that he makes in those 8 attempts. Okay, so feels like a success would be a made shot, made free throw, and a failure would be a missed shot. Okay, we'll go ahead and just assume this here. We have to state it though. Each shot is independent of the next. Okay, they did give us a fixed number of trials. They said there were going to be 8 free throws here. So we're going to say N equals 8. And then S, the probability of a success. It actually didn't mention in the problem what the probability was that he makes a free throw. They didn't tell us that. And so it feels like right here is where we're kind of violating this last condition because the probability of a success was not assigned. Okay, that was not assigned there. Okay, let's go ahead and take a look at an example here on the next page talking about rolling 2 dice. So suppose that you are playing a game of chance that requires you to roll 2 fair dice and observe if you get doubles. The game requires you to perform 5 consecutive trials of the 2 dice, and we're going to let the random variable x be the number of doubles in 5 rolls. Okay, so first and foremost, it mentions here that is x a binomial random variable? Okay, so before we can really use any binomial formulas, we have to make sure that we have classified this as being a binomial random variable. So we'll go ahead and run through this here quickly. Feels like a success is getting doubles, and a failure would be not doubles. Okay, yep, independence. We're going to say each roll is independent of the next. Okay, number of trials. I believe it mentioned we're supposed to do this for 5 consecutive rolls, and then we need to figure out what is the probability in one roll of 2 dice getting doubles. Okay, well, when you roll 2 dice, we have 36 possible options, but of those 36 options, only 6 of them would be doubles, like double ones, double twos, all the way up to double sixes. And so the probability of getting doubles of one roll of 2 dice would be a 1/6 chance. Okay, so I'm going to go ahead and abbreviate here. Number of trials is 5. Probability of rolling doubles is 1/6. Okay, so this is definitely meeting the criteria for being a binomial setting. So now we can move forward here and we can see if we can answer the question. When we see what's the probability of x equaling 0, that means we want to know what is the probability that if you were to roll 5 consecutive rolls, you would not get any doubles at all. Okay, so that means there's no success in those 5 trials. It's one failure after another, 5 times in a row. Okay, now keep in mind, a success rolling doubles is 1/6, so the likelihood of the not rolling doubles, that's the complement of that, that would be 5/6. So we could multiply 5/6 times itself 5 times in a row, or we could write this as 5/6 to the 5th power and say that it's roughly 40.19% chance of rolling 2 dice 5 times in a row and not once getting doubles. Okay, the problem starts to get more and more complicated the higher your random variable becomes here. Okay, so now we're asked, what's the probability that just one in those 5 rolls would we get doubles? Okay, and so as I start to kind of write out what those different options might look like, I could get the first 4 rolls could be not doubles, but then the last one could be the one that was doubles. Or the first 3 could not be doubles, and then the third one is the one, the fourth one is the one that's doubles. And so you can kind of see what I'm doing here. I'm just kind of shifting where the success is occurring here in the 5 tosses. Okay, so there are technically 5 different combinations, 5 different ways that you could roll 2 dice and one of them be a success. Okay, so I'm going to put a 5 there in front. Okay, now remember, the probability of getting a success is 1/6. We want the other 4 to be failures, so 5/6, I'm going to put the exponent of a 4. Now, this is just a coincidence that this particular answer comes out to the exact same probability that we have here for none of them being doubles. Okay, but I want to focus on this 5 right here. We call that the binomial coefficient. You know, coefficient generally means the number in front of our variable when we're talking about algebra. This binomial coefficient is describing, you know, how many different combinations were there that met this criteria of having one success in 5 trials. There is a formula for the binomial coefficient. Okay, you're going to see it written just with parentheses and then an N and an X. Actually, on the formula sheet that you're given for the AP test, that is this part right here. But that in and of itself doesn't actually tell you what the formula is. The formula is really this right side here where you see these exclamation points. Those exclamation points in math are referred to as factorials. I'm just going to have you make a quick label here that the n is representing the number of trials, okay, and the x represents the number of successes in those n trials. So for this problem up here that we did, we were looking for 1 success out of 5 trials. So I would put a 5 here and a 1 here, and then I'd kind of put parentheses around that. Now, how to get, remember, this is giving you this 5 that we got up here. How to work through this with the factorial? Well, I would plug a 5 here with an exclamation point. In the denominator, I would do a 1 with an exclamation point, and then 5 minus 1 in parentheses, which that, of course, would end up reducing to that. Okay. What a factorial is in math, it's where you take the number and you keep multiplying it by one number less than it until you get down to 1. So 5 factorial means 5 times 4 times 3 times 2 times 1. 1 factorial is just 1. And then 4 factorial, you can see I have that written there. Okay. So if I were to kind of cancel out those 4 times 3 times 2 times 1 in the numerator and denominator, I'm left with 5, which is the exact number we got up here when I actually wrote out those 5 different combinations. Now there's a slightly quicker way here on the calculator. There is a feature called NCR. Okay, and where that's located and how it works is the n is still the number of trials. And so what you would have to type in first is you'd have to type the number of trials. In this case, you'd type a 5. Okay, then you would press the math button, bump over to the probability menu, and you should see the option listed there, NCR. You're going to select that, and the last entry that you're going to put in is the R, which to us the R is technically our X. It's the number of successes, and in this problem that was only 1 success out of the 5. So you have to start with a 5, then you go through these key punches and end with a 1, and it should spit out that 5 that we got when we did the formula with the factorials, or when I actually wrote out the 5 different combinations there. Okay, the number of combinations really grows here. So I want to take a look at trying to do this if we wanted to now say, what is the likelihood of rolling these 2 dice 5 times, but now 2 of the 5 times are doubles? Okay. I'm not going to want to write out all these combinations. There's going to be a lot more than 5 combinations if I'm going to introduce 2 S's into this situation, which is what this is implying. Okay, so I'm going to go ahead and use my formula here, the probability that x equals 2. Okay, I'm using this formula right down here that I have boxed in yellow because that's how it looks on the formula sheet here. Okay, now this is going to be 5 trials, but I want 2 successes. Okay, now let me just break down this formula just a little bit for you here. Okay, we know that this part we can use NCR on our calculator to get that binomial coefficient. The P represents the probability of a success, and then the 1 minus P is actually the probability of a failure. And you'll notice that that's exactly what we did up here. We put the probability of a success, and we made the exponent the number of successes that we were wanting, and then we followed that up with the complement to that, the probability of a failure, and then the exponent on that was all the other remaining trials, so that these 2 exponents should always total this is just a coincidence, not your coefficient here, but they should total the total number of trials, in this case the 5 rolls that you're going to be doing here. Okay, so I'm going to fill in 1/6 here for the probability of a success. This time I want 2 successes and I want 3 failures. Now for this part I should definitely do NCR on the calculator. If I do that, I discover that there were actually 10 different combinations for me to have 2 successes and 3 failures, and that comes out to 16.08% chance there. Okay. All right, let's try one last example, and this is also going to allow me to show you one other feature on the calculator here. Okay, so I just put this same formula that's on the formula sheet here. I should also just mention this formula only works when the probability that you're being asked to calculate is an equal to probability, not a greater than and not a less than. Okay, so we're going to go back to a different basketball example where we're talking about a basketball player. It says this particular basketball player has a 60% chance of making her free throws. Suppose that each free throw is independent of any other free throw. She's going to attempt 10 free throws, and we're going to let X be the number of shots that she makes out of 10. Okay, once again, before we get too far ahead of ourselves, we need to confirm that this is actually a binomial random variable. I have no business using the NCR or this formula here if I haven't first shown that this is actually a binomial random variable. So we're going to call a success a made shot, and we're going to call a failure a missed shot. Okay, it mentioned that this was independent, so I'm just going to write down here that independence was stated. Okay, the number of free throws, that's fixed at 10, and they told us the probability of her making a free throw is 60%. So all those check off, we're good here. Okay, notice that the directions now are asking us find the probability that she would make 6 free throws out of the 10 trials. Okay, now this problem is asking us to use the formula, which is what's in that box above, and then I'm going to show you a calculator shortcut here. Okay, so let's start with the formula. Okay, the formula would be probability that X equals 6. Okay, and then I'm just using this formula right up here. The number of trials is 10. The number of successes I'm looking for out of those 10 trials is 6. Probability of a success is 0.6, and I want 6 successes, so I'm going to make the exponent on that a 6. Probability of a failure would be 40%, and then the exponent here needs to be the remaining trials. So these two exponents always have to total the total number of trials. Okay. Now, we learned before, though, to get this, we have to use the NCR feature on the calculator. That comes out, there are actually 210 different combinations of getting 6 successes out of 10 trials. Okay, and the odds of her making 6 free throws out of 10 is roughly a 25.1% chance. Okay, now I'm going to show you a calculator feature, even more kind of beyond the NCR feature. Okay, and this is called Binomial PDF. Okay, it's a PDF. The P is precise. That stands for, you're finding an equal to problem, not a greater than or less than. Okay, it requires 3 inputs. Those inputs are the number of trials, the probability of a success, and finally the number of successes that you're wanting in those n trials. Okay, so if we were going to go ahead and do it on the calculator this way, we would write out probability X equals 6, and just like we did with normal CDF, this is binomial PDF. When you use these calculator features, you always have to label your calculator inputs. So you'll put an N here, number of trials is 10, P here, the probability of a success, a made shot, is 0.6, and then X here, the number of successes. We're looking for 6 made shots. Comes out to an answer very close to what we got with the formula, 25.08. Okay, the last thing I'm just going to look at right here is you'll notice I filled in a probability distribution for you. And the way that I got these probabilities underneath here is I kept using this calculator command, but I kept swapping out this last number here for the number of successes for a 0 and then a 1 and then a 2 and then a 3 to get what each of the probabilities would be for her making no shots all the way up to the odds of her making all 10 shots if she's a 60% shooter. Okay, and then I just converted that over here into kind of a probability histogram. Okay, we will go ahead in the next video and pick up then with how to calculate, how to find the probability that she makes at least 5 free throws here. Here are a few problems you can try.